Next up is Jan from Edge Impulse, and he's going to tell you everything about AI on the edge and in constrained devices. Enjoy his talk.
Hi, I'm Jan, and welcome to my session at the Things Conference, Machine Learning on LoRaWAN Devices. So, my name is Jongboom. I'm the CTO and co-founder of Edge Impulse. We're a machine learning startup. I have a very long history with the Things Network and the Things industries. I think being involved already since 2015 and being fortunate enough to have spoken at every The Things conference so far. So this was last year, obviously a lot more fun. We were there in person. We had Johan Stocking, the CTO of the Things industries and one of the initiators of the Things Network, actually dressed up in a sheep costume and showing what the power of machine learning can do for LoRaWAN devices. Unfortunately, we're not at an in-person event, so I can't really dress Johan up in a sheep costume and have him in my house. Lockdown is still in place. But in the next 15 minutes, I'm going to try and show you what machine learning actually adds to LoRaWAN deployments and how you can get started doing that. So if we think about the type of solutions that are really easy to build for IoT devices or for LoRaWAN deployments, we realize that there's a couple of things that are really easy. For example, determining what the current temperature is. And why is that easy? And why is that kind of always the 101 example that everyone builds when they're doing their first LoRaWAN deployment? Well, because you can just buy a thermometer, a digital thermometer or an analog thermistor, connect it to your development board, read that value, here's -10 Celsius, and just send that to the Things Network. Really easy. And this is the reason why there's so many devices that just do relatively basic things. Just read sensor values and then send it off, because it's an easy task to accomplish. It's easy to calculate the amount of processing power that you need or the amount of energy that we're going to use when operating this device. However, there's a couple of things that are also useful but are much, much harder. For example, if I have a person in a sheep costume and I want to know whether that person says "bah" or not, incredibly hard. Because there is infinite number of sounds all around us, and discerning from every single one of those potential sounds whether you heard someone saying "bah" yes or no is tremendously hard. However, I do think that that is also the interesting part of lots of deployments are. If the only thing you can do is get data where there's actually a complete and accurate sensor that can help you to determine that is not a very interesting deployment. I think for the really high value use cases, not just knowing that a sensor is moving, but rather why is the sensor moving? Is it because it's being transported? Is the sensor on a ship or on a car? Something that's really hard to do if you just have an accelerometer and try to measure the peak and average motion. Really hard, but much more interesting if you know where that is actually at. Similarly, with really high resolution data like sounds, for example. What do I hear? Do I hear glass breaking? Super interesting in home security. Do I hear birds tweeting? And if so, what are those birds? Really interesting for conservation. Or images, like if I have a sensor sitting somewhere in the field in Africa and the sensor can actually know if it sees an elephant, yes or no, incredibly powerful stuff, but really hard to actually write out. So think about that. Like if you currently have a sensor in the field, imagine how much data is actually being gathered by these sensors, but then just thrown away. And this might be data that might not look interesting to you. Maybe you collect temperature data quite often and you just send a message when it reaches a certain threshold. Or maybe you have an accelerometer and you just send a message when you send the average motion to see if there's something wrong with the sensor. Think of all the data that you actually collect or could be collecting, but currently throw away and not do anything with. It's probably quite a lot. Like we see 99% of sensor data just being discarded. And why? It's not because we don't think that data is potentially valuable, but there's cost involved with actually shipping data somewhere. And very relevant to LoRaWAN devices, there's bandwidth and power constraints. Even if I think that in all the audio that my sensor captures and all the accelerometer data that I get, that there's valuable information, I can't just send that to a central location because, well, I have uplink and downlink considerations as well as power considerations. Lots of these devices are backed by a battery, and I can't just start sending raw packets through because I'll drain my battery in a day. So we need to push this logic to the device. That's the only way that we can actually put some intelligence in our deployments. And the way that we can do that is through machine learning. And don't think of machine learning as this magic black box where you have data centers full of GPUs crunching numbers. Think of it as a different way of writing your software. And when you do that, you start realizing that we can actually do this on battery-powered devices relatively easily. So I see machine learning as a way of writing my application at a moment where I don't have the rules yet. If my input is my temperature sensor and it's mounted to a fridge, and I want to know when, or cold chain management system, and I want to know when the temperature in the fridge is above 7 degrees Celsius because that is a hazard, and I want to be alerted. It's easy. You have the temperature data here. Your rules are simple. If temperature is above 7 degrees, then the outcome is send a message. If it's below, then don't do that. Machine learning lets you write this in a little bit different way. So rather than having the rules set beforehand, you give the inputs and the outcomes. So your inputs in this case, for a simple use case, could be temperature is 8 degrees. Outcome should be yes, send a message. Temperature is 10 degrees. Outcome, yes, send a message. Temperature is 6 degrees. Outcome, no, don't send a message. And the machine learning algorithm will then find those rules for you. Afterwards, actually, if your data is this perfect and this simple, the machine learning model will in the end find the exact same rules as you have. That also means that it can execute it just as fast as your microcontroller can do it today. The real power naturally comes here when you have data where it's really hard to find these rules on your own. Like I have 16,000 samples here, and someone says meh here, and I have 16,000 other samples, just audio data, and here it was not meh. Find me the rules that most accurately map from the waveform into did I hear X or did I not hear X? So the cool thing here is this processing, finding those rules is really takes lots and lots of energy. But the nice thing, you can do that once, you do that somewhere in the cloud. But afterwards, that rules is in essence just mathematics, and that's something devices can run really, really efficiently already. And in that sense, it's not much different than just a normal sensor library that you use to talk to a sensor. So we see super wide applicability for this type of stuff. So as said, Edge Impulse is a startup. We see lots of companies trying to apply machine learning to sensory problems and run this on really tiny devices. So stuff around recognizing sounds, biosignal analysis, a really big one, detecting abnormal vibrations, and even, as we're going to show in a little bit, classifying images. Anything where you have messy, high-resolution sensor data, that's a place where machine learning can help you find these rules more efficiently. And even in the TTN ecosystem, this is being used already quite a bit. So the guys at Q42 with Hector Poacher are actually making camera traps that can detect poachers from afar. Super interesting use case, and these have to be battery powered because you can't have someone actually go, or even solar powered, you can't have someone go into the field and swap out batteries once a day in the savannah. One of the other projects that we were involved in is Elephant Edge. I think if you saw Adam Benzian's talk around that, super interesting way on how we can protect elephants using technology. And machine learning can help there actually determine what elephants are doing and whether there's a threat for them. Or even in industrial work. So IRNAS, one of our partners, is working on power line monitoring, where they take current and motion in and then detect power line fires already the moment that they start happening and being able to alert someone. Really interesting use cases. So where does Edge Impulse fit in? And what are we doing here? Edge Impulse is literally the place to build embedded machine learning models. Like the Things Network is the place to build your LoRaWAN systems. It's written by engineers for engineers, helping you every step of this way from starting with data collection. So what do we actually need to build a machine learning system? To modeling your data, to verifying that what the data is actually suitable for machine learning, to finally deploying that to your device. It's been rapidly growing, super proud of that. We've over 10,000 real ML projects already created, and we literally launched 11 months ago at the Things Conference 2020. So if you're interested in machine learning on embedded systems, go to edgeimpulse.com, sign up, it's free, and start building these models. So as an example, let's just build one of these use cases, an elephant tracker that knows visually whether we see an elephant, yes or no, and relay that data to the Things network. So the first thing we'll need is some hardware. So what I have here is a new dev board made by Arduino in their Pro line. It's the Portenta H7. Really cool, nifty, a really tiny little dev board that is incredibly powerful. So it has a microcontroller on it from ST and has an M7 core, a high performance core, and an M4 core, Cortex M4 core that we can run applications on. And we have a vision shield. So that's a little shield with a very tiny little camera. I hope you can see this from on the feed. But there's a small HiMax camera on it. It's actually monochrome, but it's good enough for the use case that we're trying to solve here. And we just start collecting data samples. So in edgeimpulse, we have really nice tools to actually get data straight from this board into our data collection pipeline. But if you don't have it, snap a couple of photos with your phone and upload them. No support there. This model, the model that I just built here to detect between elephant or no elephant, very interesting case when I deployed this on the Savannah, took about 200 photos. And that collection phase can be done in 20 minutes. Then we help you train a model. Think of this as finding all those rules in an automated fashion, and we really help you do that in nice visual tools. And finally, what you get out of that is a C++ library, just a normal library, very similar to how you integrate any other sensor. So think of it as a driver, but rather than get a raw camera feed or raw accelerometer data, you get a conclusion out of it. This was an elephant, yes or no, or I saw weird motion, yes or no. Just integrate it like any other sensor. So I mounted this on my desk, literally just put it on there, and I had a toy elephant, the one that you saw here on the previous slide. That we first put in front of it, labeled it as we saw an elephant here. And then we use the LoRa radio that is sitting on the vision shield, really tiny little one from Murata, to relay information whenever we see something different. The nice thing is you can do this very low power, by just not sampling all the time. If you know that elephants are slow animals, then maybe you can sample once a minute and be asleep the rest of the time. So you can do this really efficiently. So let's take a look at the demo. So you'll see the feed from my webcam here. So this is my living room. First unknown, I put the elephant in front of it. It immediately spots that. So we use a moving average filter to discern that. We send that message straight to the Things network, knowing, hey, we saw an elephant. Then it switches to unknown again when I'm there. And finally, when I'm in focus, it's actually a bit unsure. Is that an elephant? Is it something completely different? With discerning that. So super trivial and not different than writing code currently to read a temperature value and send it to the Things network. No, much rather you have a complete library that now knows what's happening in front of you. So this project, the one that I just presented, is open. You can just go to that URL, look through my data set, look through all the intermediate steps. There's also a firmware, so if you're in a Portenta board, use that. And just to show how small this can be, this is actually doing image recognition in real time on a microcontroller. We can do this in 45 milliseconds in 150K of RAM, and we can go down much, much lower for audio or vibration models. So a recap. First of all, the machine learning hype is real. It's possible to build real machine learning models using real data and deploy them to real devices already today. We have lots of customers doing exactly that, and it fits on your typical LoRaWAN sensor. Super powerful. I also think that machine learning and LoRaWAN are an absolute perfect fit because we often run with lots of constraints in mind on our devices. And being able to use machine learning to actually discern what is happening around us is a super, super powerful tool without ever having to go to the network. So perfect fit there. So you already watched this talk, so I think you're motivated to actually do this. Let's actually make all our devices a lot more useful. Go to edgeimpulse.com, sign up. We have lots of tutorials also on building vibration and audio models and how to communicate that back over LoRaWAN network. So I can't wait to see what you build. And I hope to see you later today at one of my workshops as well. Thank you.